underlying theory. So today we're going to hear about linearly qπ-realizable MDPs, and the stage is yours, Gellert.
Cool. Thank you, and thank you for the opportunity to present this work here. The title of the work is that online RL in linearly qπ-realizable MDPs is as easy as in linear MDPs if you learn what to ignore. And the caveat will be that learning what to ignore will not be trivial. And this is joint work with András György and Csaba Szepesvári. So I'm going to jump straight into it, but please ask questions if there's anything that's unclear, because I think the details might get a little bit difficult, and anywhere else as well you have questions, please ask them. Okay, let's see if I can make the slides go. Okay, so high-level motivation, just very quickly. RL is a general framework for sequential decision-making under uncertainty, and it is so general, in fact, that there are some issues you encounter when you practically try to deploy RL algorithms. Some of the problems that you might encounter is that it's very hard to explore well. And known RL algorithms sometimes just collect loads and loads of data without doing anything kind of smart before they see any rewards. And of course, what you have to solve for these kinds of large real-world deployments is you have to solve the generalization problem. You have possibly infinitely many states, but you have to kind of learn about them at the same time. You can't individually learn about them. So you kind of have to solve this problem. And so what we're looking at is we're trying to understand when this generalization can work. And in particular, we're looking at function approximation to understand, to approximate Q values. And within that, we're looking at linear function approximation and the conditions that allow you to get sample efficient RL and the conditions that aren't enough. So that's kind of the motivation for this kind of work. And during this talk, we're going to talk about finite horizon RL, so capital H horizon RL with features. And I'll explain what the features are, but first, the finite horizon part. So you have an MDP. I'll go very quickly over this, but if it's too quick or if it's boring, then I do apologize. So you have a Markov decision process, which we denote by MDP. And this is kind of the environment. It represents the environment. And then you have a policy pi, and they together define a random trajectory. This trajectory starts with state S1, and S1 is a fixed initial state. So this is like a designated initial state. And then you take action A1 according to your policy pi, and then you observe rewards and a next state transition. And then you take another action, and so on and so forth. And you do this until you get capital H many rewards. And that is at that point, the horizon ends, and a new episode starts again from this same start state S1. And the notation will be that the state value function for a policy pi is V pi of S, which is going to be the expectation when you start from state S and follow policy pi onwards of the sum of rewards that are still left in the episode. And for this, we introduce this stage function that maps states to whichever stage they're in. So you look at the reward associated to the next reward until the end of the episode. And you sum it up, you look at the expectation. That's V pi. You have Q pi, which is the action value function, which is the same thing, but here you start at state S. First action is A, and then you follow policy pi, and you look at the same expected sum of rewards. And then V star and Q star are the optimal versions of V pi and Q pi. So for the optimal policy pi, what is the V pi and Q pi value? Then the goal of this RL problem is to find a policy pi that is up to epsilon worse than the best at this designated initial start state S1. So your V pi of S1 needs to be at most epsilon worse than V star of S1. And then we call this policy epsilon optimal. And if you can find one of them, then you have solved this problem. And we're also going to look at solving this problem in an online fashion, where you can interact with the MDP, as it is shown with these trajectories, by choosing the actions. But you cannot reset to any state of your choosing, and you cannot use a simulator to like look at many different possible interactions you could have had from that state. So you always have to like restart an episode from the start state. That is the framework in which we're looking at this problem. And yeah, so that's the finite horizon part. And then the features part is that, recall that like you might have loads of states, possibly infinitely many states. And it wouldn't work to learn about individually about all of them. So we need to kind of compress them and encode something important about them. So what we do here is we say that for each state action pair, there is a feature which we denote by phi of SA, which is going to be just a d-dimensional vector. And this is supposed to represent everything that's important about that state action pair. And if it does actually, in fact, represent everything that's important, then the hope is that you only need to learn with your algorithm about this d-dimensional space. And the d is assumed to be a much more manageably small number than the number of states or number of actions. So you could have you could actually just feasibly learn about those parameters, and that's the idea here. So for a little bit of background, there is a reason why RL is fundamentally harder than bandits or supervised learning, and this is because even when this like optimal action value function Q star can be represented as a linear combination of the features, even then it is statistically very hard to learn to solve the problem. And this is because, unlike with bandits or with supervised learning, these optimal targets, which in this case are Q star, are not revealed with every interaction. So when you choose, an action in a state, what you observe is a reward and the next state transition. But you don't observe what the Q star or V star would have been from that next state. So it's really hard to know what the Q star should be, even just to get, one approximate estimate of it. You would have to know how to act optimally from the next state onwards. And because you don't know that, it's really hard to start learning. It's kind of a chicken and egg problem. You would have to know how to solve the problem from the next state onwards to be able to learn for this state. And so this makes it statistically very, very challenging to learn, like exponentially so, exponentially hard to learn with this structure. And so this is the background. This was known before. But then the question is, if we take a step back, look at what practical algorithms do and how they can learn, they clearly can learn in a lot of cases. What we find is that algorithms like DQN and policy gradient, they approximate qπ for various policies pi. So they go through some policies, and they always try to approximate the qπ values corresponding to that policy. And maybe they do this with some neural network, in which case the underlying assumption is that a linear combination of the neural network's final layer can express the qπ. Gerger, you have a question? You're muted.
Yeah, right. Yeah, sorry. So does a DQN really do this though?
Yeah, well, I mean, I think it does learn Q values.
It learns Q star, right? But I guess maybe a better example would be some actor critic algorithms.
Right. Yeah.
Yeah, like a DQN tries to approximate the Bellman optimality operator.
Yeah, but it learns. Okay, it learns. It like progressively learns. I guess maybe that is the point of this slide. There is some progressive learning happening, which isn't captured by just the Q star realizability assumption. And okay, so what we assume isn't exactly the same as what these algorithms, like that the underlying assumption is. We make this kind of simplifying assumption, which is going to be that we fix features, which kind of corresponds to, if you like, the setting where you pre-train some neural network and then fix all of the layers up to the final layer, and then kind of fine-tune that final layer to get you all kinds of qπ functions. And this setting, it corresponds to fixing the features and then assuming that a linear combination of them can express all qπ functions. So this is what we're going to look at, and I'm going to be a bit more precise on this. But then the question is whether this is provably sufficient, this kind of structure, for sample-efficient online RL. And the answer will be that yes, it will be sufficient. And the challenge that has to be resolved is of course the exploration challenge. So imagine a setting where you interact with the MDP and you don't yet observe rewards. And all you see is what the features are. And based on these features, you have to decide whether they look informative. And if they look informative, you have to learn how to keep getting back to informative state action pairs. So it's not just as simple as figuring out that a state action pair is informative, because remember, we don't have a simulator. We can't just reset and play that state action pair multiple times. So we kind of have to learn how to get back to informative states. So that's going to be the challenge of this work. So to summarize the contributions, there are like the two kind of main linearity assumptions that this work relates to is the qπ-Realizable assumption and the linear MDP assumption. And I'm going to define what they mean. But the first contribution here is to characterize the difference between the qπ-Realizable and the linear MDPs. And the difference will be that the former, the qπ-Realizable MDPs may have these zero-range states where it doesn't matter what action you take. So they are kind of irrelevant states, but they somehow are these like additional states that might be in the qπ-Realizable MDPs. So that's the first contribution. And then the second is using this. We showed a first algorithm that can solve these qπ-Realizable MDPs using a number of samples that is bounded as a polynomial in the relevant parameters. And previously, for this, you needed at least either the assumption of linear MDPs, which is a stronger assumption, or resettable, kind of like a simulator. And so now you basically don't need either. So that's going to be the new algorithm. So I want to define what the linear MDPs are, and then I want to define what the linearly qπ-Realizable MDPs are. And for the purpose of this work, there is going to be a slightly different definition for linear MDPs than what you might be used to. And this was necessary for very technical reasons. But the point is that all of the algorithms I'm aware of, they use only this property, these A and B properties of linear MDPs. So this is what we're defining it as today.
So this is the implication of the usual definition.
Yeah, so it is an implication of linear MDPs.
Why is it not equivalent?
There are some very technical reasons, and I always forget. But if you try to show...
For example, if you look at the second one, I usually, if I remember, usually it's something like if you look at all possible f's, I think you can just let f to be those indicator functions, right? Then that would probably recover the usual transition matrix decomposition.
Yeah, like if I remember correctly, the problem is for like when you have infinitely many states.
Yeah, sure. Yeah, I'm always only worried about the finite states. So yeah, sure.
Yeah, but it's basically this. It's basically this. It's that there could be some technical issues if you want to get the full generality of the linear MDP definition. But basically, this is all that the algorithms use anyway that use linear MDPs. So I thought to define it like this. So yeah, two conditions need to hold for linear MDPs. First, the rewards need to be linear in the sense that there is a parameter, theta. And by the way, this is a separate parameter based on each of the stages from 1 to h, but doesn't really matter. The point is this parameter doesn't depend on S or A. It's just a d-dimensional vector. So there exists this parameter such that for each state action pairs, the expected reward you get for that state action pair can be written as an inner product of the feature for the state action pair and this theta. This is the condition A. And the condition B, that transitions are linear in the sense that for any function f that maps states to values between 0 and h, the expected next state function value is also linear. So there exists a parameter theta corresponding to this f, such that the expected next state function value is linear in the same sense as it was before. And so if both of these hold, then we have a linear MDP. And an entirely different assumption altogether is a qπ-Realizable MDP assumption. And here, the qπ functions for all deterministic policies pi are linearly realizable. And what I mean by that is the same thing as before. So for each policy pi, there exists a parameter for that policy such that the qπ function can be written as this inner product. And the point is, in all of these cases, the kind of point is that you can learn the parameter, which is just a d-dimensional vector. And suddenly you have learned about the whole state action space, right? Because the features are revealed to the algorithm for each state action pair. And you only had to learn about the D parameters to know of all of the qπ, or the expected rewards, or the expected, f of s prime. So the point is this should make learning feasible. So these are the two assumptions we're looking at. And the first thing that I want to say is that it was known before that linear qπ-realizability is a weaker assumption than linear MDPs. And this holds in the sense that every qπ-realizable MDP is also a linear MDP, but not vice versa. And the new result here is that the linearly qπ-realizable MDPs are the same as linear MDPs, with some additional zero-range states present in them. And so here we say explicitly what the range means. The range of a state S will be the maximum Q difference that the choice of the action can make in that state. So we're taking maximum over action A and alternative action B, but also over policy pi of the qπ of taking the better action minus the qπ of taking the worse action. And so this, you can think of it as the maximum regret you could possibly encounter in state S. And if the range is 0, that means it never matters what action you take in terms of the Q values. If the range is small, it matters. It means that it has a very, very low impact on the Q values. So in either of those two cases, it doesn't really matter what you do in state S, so you should just ignore it. And that's kind of the upshot of the whole work. So the strategy is to identify and skip over these zero-range states that don't contribute anyway to the Q values. And actually, for technical reasons, we don't just want to skip zero-range states, but we also want to skip low-range states. Like, at the end of the day, we only need to get an epsilon optimal policy. We can lose a little bit of optimality by skipping low-range states as well. So the idea is that on the left here, we have an MDP that's qπ-realizable. And what you have a choice of up and down initially. And the choice of up gets you a reward of 1 and then gets you a reward of 0. The choice of down gets you a reward of 1/2 and then gets you another reward of 1/2. So what the point of this is that from the perspective of Q values, it doesn't matter whether you go up or down. You will end up getting 1 in total in reward. But from the perspective of transitions, the up and the down have a different transition. So you can parameterize it. You can give features to this MDP that are one-dimensional, that will make it qπ-realizable, but not a linear MDP, because they cannot distinguish between the up and the down action in terms of their transitions. So this is, on the left, a qπ-realizable, but not a linear MDP. So now if you take S2 and S3 and say that they are zero-range, and you skip them, and by skipping them, what we do is we just sum up that we take the first available action from them and sum up the rewards along the trajectory that we skip. Then we reach the MDP on the right. And here you have, on the right, 2 equivalent actions that both go to the same state and get you the same reward. So that is already a linear MDP. So the idea is that you identify and skip over these red states to then get a linear MDP, because we know how to solve linear MDPs. So this is the overall strategy. But to show that it kind of works, or that it has some merit, we first have to show a new tool. And this might be of independent interest. For this, we call a function nice if for some absolute constant capital C, which is fixed and doesn't change, and it's just a constant. If the function maps states to values that are an absolute value bounded by C times range of the state, then the function is nice. So this means it needs to map 0 to zero-range states, and it has to map a value to low-range states. So if the function is nice, then it's like the expected next state value is linearly realizable. So this is the tool. This is the new result. And contrast this with the linear MDP assumption, the assumption B. The only difference is that red box. So with the linear MDP assumption, you needed this to hold for any function f that maps states to numbers between 0 and h. And what we show here is that this holds for any nice function. So maybe fewer functions, but a similar structure that we show. And the idea for the proof is to fix some nice function f, and some state action pair SA that goes to transition S prime. And because of the definition of the range of the S prime, there is a good action and a bad action available from S prime with a policy pi, such that the q pi of the S prime and the good action minus the q pi of the S prime and the bad action is exactly the range. So if this holds, then there are pi plus and pi minus slightly better and slightly worse policies, such that the v pi plus on S prime minus v pi minus of S prime is exactly 1 over c times f of S prime. And this holds because the function is nice. That means 1 over c times f of S prime, at least an absolute value is at most range. So you can kind of like probabilistically mix the better and the worse action in such a proportion that it gives you exactly f. And by the way, if f gives a negative reward, then the pi plus will end up being the lower, the worse action, and the pi minus the better action. But in either case, you can make this happen just by mixing the better and the worse actions. And if this equation 1 was satisfied for all possible S primes, for all possible next states, then we would have this kind of red equation hold. The q pi differences would be exactly the expectation of the next state f value times 1 over c. But the problem is the way we constructed pi plus and pi minus was for a specific S prime. So it doesn't quite work immediately, but it turns out we can easily fix this because we can map all of the possible next states to one of n, where n is finite, number of buckets, and construct, for each bucket, we can construct a pair of policies pi I plus and pi I minus for bucket I, such that they do the same thing on states that do not have this as their corresponding bucket, do not have I as their corresponding bucket, but they only make a difference for states that that correspond to the bucket that this pair of policies is constructed for. And for those, they make a value difference of 1 over c times f of S prime, as they did before. So if you have this, then you have only these like n number of pairs of functions to sum up. So like you sum their q value differences, and you get the 1 over c times the expected next state function value. And if you have this, it's very simply just a matter of plugging in the realizability assumption. So you plug in the parameters for the q pi I plus and the q pi I minus, and the sum of their differences scaled up by a factor of c will be the parameters that realize this expected next state function value. So this is how you prove just very quickly this tool. And then the next question is, okay, so how do we use this tool? Recall what we wanted to do is we wanted to skip the low range states. By the way, if there's any questions about the previous slide, just please, because maybe I'm going a bit fast now. But yeah, just please ask. Otherwise, I'll carry on. So yeah, so we proved the tool. The tool says that like any nice function is realizable. And what we want to do now is say that if we could skip the low range states, then the resulting MDP would be a linear MDP. We're going to prove this on this slide. So we construct from MDPM an MDPM prime that skips the low range states. And again, what that means is take the first action and sum up the rewards along these like paths that you skip. So first, let's note that near optimal policies for M are roughly the same as near optimal policies for M prime, because we only skip the low range states. So we don't mess up any policies near optimality too much. And also M prime stays linearly qπ-realizable. So then to prove that M prime is a linear MDP, we use the tool and the fact that there are no low range states to say that like now every function is nice, right? Because there are no low range states. That means every function that maps to 0 to h is going to be also nice. So therefore, we have the condition B of the linear MDP assumption. And using that, plus the fact that the M prime is qπ-realizable, we can also show that the rewards are linear. So that gives us the full linear MDP, both A and B conditions. So then M prime is a linear MDP, and we can solve it with algorithms like Eleanor. But of course, the complication is that it is hard to identify these red low range states. So the final solution isn't going to be exactly a case of finding these and skipping them, but it's going to be a case of modifying Eleanor. Johannes, you have a question?
Question. We can just directly ask.
Mm-hmm. So I just wanted to clarify, if you need to apply this tool recursively, like, do you have to look for like low range state in the new MDP and then also remove them, or you only do it once and that's enough?
So in this, for the purposes of this slide, I am magically gathering all the low range states and removing all of them and proving that if I did that, then I would end up with a linear MDP.
But that means like if there's still a low range state once you did it once, like once you remove all the low range states in the original MDP, you would continue removing the low range states in the new MDP. So like in your example, like M prime still has a low range state.
So what I just define the range of a state on M, and then I don't change it. So then there is a set of low range states, and the rest of the functions, the rest of the states are by this tool going to be. So basically, this tool that shows this, it will hold for the MDP M prime as well. Because you still have the original realizability condition. So you don't start again with that M prime MDP and have like only the policies on them being realizable. So the point is you don't have more states being added to the low range set. You just have it initially, and then you remove those, and then what you end up with is a linear MDP. Does that make sense?
Yeah, it makes sense.
Yeah. So what I mean is there's no low range states left. In the sense that those states that are left are not low range in the original MDP, and that's what you care about. Yeah. Good point. So it's hard to identify these low range states. So instead of this direct kind of reduction to plugging it into Eleanor, we will have to kind of modify Eleanor. But to do that, let's actually first go through what Eleanor does. So Eleanor works for linear MDPs. For example, that's what it's the property that we'll use today, and what it does is in every iteration, it runs a policy selected optimistically, and we'll talk about how it selects this policy optimistically. But it runs this and it collects more data, and so it adds all of the data it collected to this growing data set, capital D, and it will then compute optimistic parameters, which are these theta bars. And these parameters optimistically estimate Q values. So that's their point. And we do this stage by stage backwards by using bootstrapping. So for a partial trajectory ST onwards, we get the Q tilde, which is going to be this like optimistic Q value estimate based on the trajectory. It's going to just be the reward plus the best possible next state's optimistic Q value, which is going to use the bar theta of t+1, like the next state. The next state's optimistic parameters. So this is how it uses bootstrapping. So once it has these Q tildes, which estimate the optimistic Q values for trajectories, we can set up linear least squares with the covariates being the features that you observe at stage t, so like the phi of st and at. And the corresponding targets will be these Q tildes for the trajectory. And then you solve this, and your theta hat will be your least squares estimator. Then you can prove that the true parameter lies within a confidence ellipsoid of this theta bar. And so you can choose your theta hat. And so you can choose your theta. Theta hat is the solution to the least squares estimator. And then you choose your theta bar, which is going to be the optimistic parameter. You choose it optimistically from within this ellipsoid. And to show how mathematically that all looks, we have the whole thing written out here. It's a whole optimization problem where you optimize over all of these parameters, bar theta. And you choose the one that will give you the best possible value from the start state. So you also look through the start action, and you look at the best inner product. And the conditions that it needs to satisfy is that, well, you have this covariance matrix for the least squares prediction, and you calculate your least square solution, hat theta, and then you choose these bar thetas optimistically to be within this confidence ellipsoid. Beta is just a constant. So this is what Eleanor does, and then once it has these bar thetas, it will define an optimistic policy based on these predictors, and run and collect more data, and so on. Eventually, it will be done. So so the reason why it works for linear MDPs is because these Q tildes are realizable. Their expectations are realizable. And this will not, in general, hold for qπ-Realizable MDPs. This is the difficulty we have to overcome. So what we modify with Eleanor is that we will call the algorithm Skippy-Eleanor. And we, instead of running policies, we run Skippy policies. And the Skippy policies, they skip over suspected low-range states. Otherwise, the algorithm is very similar. So like we have a new parameter that parameterizes which states to skip with the Skippy policy, and we are optimistic with respect to this new parameter as well. But otherwise, it's a very similar kind of process of computing these optimistic parameters bar theta, and then estimating the Q values using bootstrapping as well, slightly differently, and we'll get to it. But it's all very, very similar on a high level. Okay, the extra complication will be, of course, that we need to learn this new parameterization, this like guess of what low-range states to skip. And we have to learn this simultaneously as we progress and refine this guess as we go on. So I want to talk a little bit more about Skippy policy and how it skips states. And for this, recall the definition of the range function, which is going to be, this is the definition we used before, the Q differences, but we can equivalently use the definition which uses the linear realizability, where we just have an inner product where on the left of it, we take the feature difference of action A versus action B, and we inner product that with the parameter theta that is selected to maximize the value out of all of the possible parameters. So this capital theta is the set of all possible theta parameters that correspond to policies. So this is an equivalent way of writing the range, but it will make sense that we can write it in this inner product way. It's going to be more useful for this. So recall that Skippy policy has an additional parameter. We call this capital G, which will determine which states to skip. And G actually contains guesses for ellipsoids bounding this capital theta. So this will give you a way to parameterize Skippy policies in such a way that you don't have to give a range parameter for each state. That would be like infinitely many parameters, and you want to have a small number of parameters in a d-dimensional space, ideally. So you have these Gs that contain ellipsoids that should hopefully bound capital theta well. And based on these, you can directly convert them, these capital Gs, to these like guessed range bounds, which we call range G, using this equation 2. So instead of this capital theta, if you plug in the bounding ellipsoid that lives in this capital G parameter, then you immediately get this like range bound estimate, range G. And so what Skippy policy does is, when it is started from ST at stage T, it will skip states Si for T+1 onwards whenever this state has a low guessed range bound. And by low, I mean it has to be lower than some threshold. And so we will keep skipping these states, and at some point it will stop. And let us denote the first non-skipped stage by T prime of G. So like when you start from stage T, it will keep skipping and it will stop at T prime. And this T prime will depend on the G, of course, because the G will give you the parameterization that determines what to skip and what not to skip. So we can now get back to the algorithm and what it actually does. So it will collect data by running Skippy policies that are parameterized by G. And also, this is going to be still important. So like I wanted to put it here again, that T prime G is the first non-skipped stage after T. And then how do we change this Q tilde estimator for a trajectory? Well, we basically add up the rewards along the skipped states. And then we add the whatever state, the first one that we didn't skip, the optimistic predictor's value on that state. So it's still using bootstrapping. And in fact, if you want to see the equivalence with Eleanor, it's if you don't skip anything, So then the t prime will always be equal to t plus 1. Then this is going to be equivalent to the q tilde that we had at Eleanor. But otherwise, it will sum up the rewards, and it will look at the next state, whatever state you didn't skip, and its optimistic estimate, and add that to it. So otherwise, it will be the same. So you still have the same optimization problem. The only thing that's different is that you also optimize now over capital G, which will determine the t prime g's, and this will determine the q hat, which will in turn determine all of the other parameters. So you run this optimization problem over one more argument. Okay, so this is what qpE-Eleanor does, and I want to now talk about the analysis of it. So what we had for the analysis of Eleanor, these points 1 and 2 still remain, and we will add an additional point. But so let's go through the points 1 and 2. What happens is at every iteration, you came up with we come up with a new optimistic policy, and then we run it, right? And so when we run it, we can measure whether it will get us an average value that is close to what was predicted. And if it does, then we are done because we predicted optimistically. So if we get close to that optimistic estimate, then we are done. And this is still the case. Then with Eleanor, we have another condition. If this doesn't hold, then the difference between what was predicted for that value, for the v pi, for the optimistic policy pi, and what we actually observed as an average outcome of the v pi by doing unrolls, the difference between the two have to be proportional to the least squares confidence sizes. So these are the sizes of the ellipsoids during these least squares predictions. And so that means by adding this data to our data set, we are shrinking these ellipsoids, and there's an elliptical potential lemma with which you can make an argument that this doesn't really happen too many times. So you can bound the number of times condition 2 happens. The idea is then eventually you will get to condition 1 and you will be done. So this is the high level analysis of Eleanor. I won't go into more detail, but I want to focus on the third condition, which we have, which unfortunately we have because these q tildes that we have, even though we did try to skip over some low range states, we may not have skipped over all of them. And so it might have been the case that the q tildes that we are trying to predict for with linear least squares are not actually linearly realizable at all. And so the problem doesn't come from a confidence set being too large kind of problem, but it comes from the fact that the underlying quantity we try to realize is not actually realizable. And in these cases, we need to detect an inconsistency between the predicted q tildes and the average rolled out outcomes. And we need to learn from that. And then we argue that this condition 3 also only happens a bounded number of times. And so then eventually condition 1 has to still happen. So that's the new part of the analysis. And I will gloss over, I will talk a little bit more about this new part, but I want to gloss over some technical details. So for example, in the paper, you will find that we don't just have this skipping being either true or false. We don't just either skip a state or don't skip a state, but instead we probabilistically skip states with probabilities that are proportional to their range. And this is because we want to make the underlying quantities smooth in their parameterizations. And we want to make them smooth so that we can have good covering numbers and these kinds of technical reasons. They make the notation a little bit harder to follow, so I just got rid of all of that. And so for us, it's either skip something or don't skip something. But if you care about the full details, then look at the paper. And also to make everything precise, you need to clip the value estimates. And also in the paper, you will find details on how to handle misspecification when the qpi isn't exactly realizable. But for the purposes of this talk, I'm glossing over all of those details. And I hope that the rest is captured properly. OK, so first, I want to talk about inconsistency, because remember what we want to do is this third condition when we can we should be able to detect some inconsistency between the predicted and the measured q tildes. And so I want to define what that inconsistency actually is. So recall that the targets of the least squares were these q tildes that for a trajectory had this kind of shape. And then we had the actual least squares predictors, hat theta. And this, by the way, is nothing new. This is just from the couple of slides before. But the xt and the yt are new. So xt. So okay, what we do is we have this like hat theta and the q tilde. We have this coming from the previous data, and based on this, we get the new optimistic policy, and then we unroll that new optimistic policy, and we get new trajectories. And those new trajectories will be what we backtest these estimators on. So the x and the y will be the average predictions for q tilde, and the y will be the average q tilde outcomes on these new data trajectories that we collect. So the xt will be the average like inner product of the tth stage, the ith, because we do this I going from 1 to n, we do n unrolls. And we always look at the average prediction for q tilde, and then we also look at the average like q tilde outcome for this new data set, and then we look at whether the difference between them is large for any stage t. And so if it is large, then that means you didn't predict well. And so if you didn't predict well, either condition 2 holds, or you detected an inconsistency. And so this is the third situation that we're talking about. If you didn't predict well and you detected an inconsistency, what do you do then? How do you learn from it? So first, it has to be said that these least squares predictors would be good if the skippy policy actually did skip the low range states. So the only reason why these predictions weren't good is because you must have not skipped some low range states. And so this is the case because these q tildes can be decomposed into nice functions as long as you don't stop at low range states. And so to see that, we write it in a slightly different form where we add all the rewards here, and the expectation of that is just going to be the q value, which we know is realizable. And then what remains is this quantity in the parentheses, which will assign some value for a state with index t prime of g. So if this t prime of g, if it never stops at a state that is low range, then this in the parentheses will be a nice function, and it will be realizable as well. So that is kind of the reason why, the only reason why you could have this inconsistency is because you stopped at low range states. So in these cases, you have to define your estimates for what the low range states are. And this is the form in which you want to learn about the world in these cases. So to define these estimates, recall again the range definition, and in particular, this like inner product form of it. And we can draw that geometrically to understand what's happening a little bit more. Imagine that you're at state S, and you have an action A or B corresponding features red and blue. And the difference between those two features is this phi prime of S. So when is the range of the state small? It is small either if this phi prime of S is like itself a very small vector, but in that case, it's obviously visible that this is a low range state. But it can also be small, this range, if this phi prime of S, though large, points in a direction in which this capital theta is very narrow. So this capital theta, which recall is the set of all parameters, could be very narrow in many directions. And if it's narrow in the phi prime direction, then that will give you a low range state. So we're trying to learn the geometry of this capital theta. So okay, let's have this phi bar prime be the largest feature difference in S normalized to unit length. And we'll think of it as the representative direction for state S. And then, okay, a little bit of context. What are we trying to do? We're trying to get this q tilde and decompose it into several different contributing factors in such a way that we decompose it to like nice functions and not nice functions. And then we try to understand which component has the largest corresponding error. That will be the component that comes from not nice functions. And somehow we will try to learn something about the shape of this capital theta as a result of all of this. So for this, we set up a weighted least squares problem that for any direction W and stage H will modify the target's q tilde to split them into many different components. So this q tilde for some direction W and stage h, we'll be looking at only, this is an indicator function, only trajectories where we stopped at stage h. And within those trajectories, we will take the phi bar prime, which is the representative direction of the state, and that we stopped at, and inner product it with this direction w, and take the square root of it. So the idea is that if this w is, so actually, let me show this first, which is basically like, what does this actually mean for inconsistencies? If you solve the corresponding least squares problem, which is going to give you the hat theta for this w, going from stage t to like this stage h that you're sensitive to with this q tilde, you solve this least squares problem. Then you can look at the inconsistency, which we defined as the difference between x and y for these like decomposed, like modified q tildes. So we define them the same way as we did before, and we look at their differences. And now we can look at the maximum inconsistency for some direction w, and starting from some stage t, and being sensitive to some other stage h. And so the idea is that if you have a w that points to a direction in which capital theta is wide, then the component in that direction will be a nice function. So if you take the corresponding q tilde for that w, then that will be a nice function. It will be a realizable function, and therefore it will have a contribution of zero inconsistency, or like basically just noise inconsistency. So therefore, if you maximize this inconsistency as a function of w, then you should find a w that points to a direction in which capital theta is narrow. And that's the whole point of this decomposing of the error signal, to find a direction in which capital theta is narrow. And once you solve it, and you can solve it because you have measured all of the information required to solve this optimization problem, once you have solved it, you can restrict the optimization domain of G. Recall that G is used for the Skippy policies, and you optimize over it. And it will contain the bounding ellipsoids for capital theta. But if you know already that this capital theta will be narrow in some direction, then you don't have to. Then you can just shrink your optimization domain over it. And by a similar elliptical potential lemma than we had before, we can show that this shrinkage of domain can only happen so many times until there is like nothing left in the domain. So that will eventually be the way in which we can bound this like third new part of the analysis. That it will only this condition, this learning, will only happen a small number of times, and eventually you will have to be done with the problem. So this is what's new about the analysis. I don't know if there might be some questions. Please ask. I mean, it got a little bit complicated, but yeah. So I think this is like all I wanted to say on the analysis, and then I wanted to just mention what the final result is, because there needs to be a theorem, right? So the theorem is that with high probabilities, Skippy-Eleanor takes at most a number of steps that is polynomial in the relevant parameters before returning an epsilon optimal policy. And this polynomial, if you look at it, it will be optimal in epsilon, but I think likely not optimal in capital H or D, right? So the kind of relevance of this result is not necessarily that we think that these numbers are looking great, but it is that it is a polynomial. So it's like the first result that shows that this problem can be statistically solved in a polynomial time. But I did want to point out that there is a gap between qπ-Realizable and linear MDPs. In fact, there are two gaps. One of them is, and we don't know if these gaps exist, or we just don't know yet, right? So one of them is that right now the best solution has for the Skippy-Eleanor takes more steps than you need for linear MDPs. And the other is that the solution that the Skippy-Eleanor that I just presented, it will not be computationally efficient. Like, we don't know if it can be made computationally efficient. And so we know that we can solve linear MDPs in the online setting computationally efficiently as well. So we don't know if this gap needs to exist, or if there's a way to make something like this computationally efficient. On this, I will say that it isn't just the case of, oh, it's computationally efficient because I used Eleanor, right? Like it's not, it is the other way around. I used Eleanor because we already had this problem that it was computationally efficient to begin with, so we might as well have used something that is quite elegant like Eleanor. And okay, so the reason why it was already computationally inefficient is because we are also optimizing over this capital G. And this capital G contains, recall these like bounding ellipsoids for capital theta, based on which we determine whether to skip a state or not. So the effect of skipping a state or not is like highly nonlinear, and it's very hard to make this optimization problem efficient. So this is kind of the underlying challenge, and it is not the case that we just use Eleanor. Like you could try to use a similar idea with LSVI UCB, but you would still have this problem, and you would still have to resolve this, like how to optimize efficiently over capital G. So yeah, also I want to point out that we can handle the misspecification where the qπ isn't exactly realizable. So that isn't, it basically, the performance degrades gracefully in the misspecification, the maximum misspecification. So that isn't a huge problem, but it is, I think, the biggest maybe outstanding question is going to be then this like computational efficiency for qπ-realizable MDPs. So just to sum everything up, what we knew already before this is that the ability for the features to represent the optimal function, optimal action value Q star is insufficient statistically for sample efficient RL. But what we know now is that being able to represent all qπ functions is sufficient. At least it is sufficient statistically. So we don't know if we can make it computationally efficient, but at least statistically it is efficient. And it is efficient in the sense that it is a polynomial, not necessarily that it is a great polynomial. And I do believe that improvements could be made on the exact polynomial. So another bonus thing that we learned, which might be kind of cool or of independent interest, is that the qπ-realizable MDPs are not that different from linear MDPs. The only difference is that like the qπ-realizable MDPs have these potential additional low-range states, and if you can figure out which one they are, then you can just reduce the problem to a linear MDP problem. So yeah, that's all I wanted to say. And if there are any questions, I'd be happy to answer them. Thank you.
Let's first thank Gellert for the presentation.
Thank you.
For the last slide, I guess I have a comment about, so I think there is an extra gap between the first and second bullet point, which is related to the third point, right? So for the first bullet point, when we talk about optimal realizability of Q star, I think that's a really weak assumption in the sense that that doesn't impose any constraint on the underlying MDP dynamics itself, right? It's purely a representation assumption. But I think what your work shows, which is somewhat a little surprising, is actually all qπ realizability makes the problem tractable by essentially constraining the underlying dynamics. Right? So it's like you're not actually working with all possible MDPs, but with just carefully crafted features. You're actually only working with a substantially small subset, an MDP from a structured subset of possible MDPs.
Yeah, while still only looking at Q values. So yeah, we don't need to necessarily learn. Yes, I think maybe the point is that like you don't need the transition structure necessarily. It's enough to have the qπ structure. But yeah, definitely this assumption is like much stronger than the Q star realizability assumption. Yeah. Right.
The other thing I was vaguely reminded, I don't know if it's actually relevant over here. I do remember. Do you remember, like in this bilinear paper? I think they have also have some positive results. I don't quite remember the detail, but
so I think there is one result I remember, but I don't know if it's the one that you are thinking of, which is the if you have the V star and the Q star realizability at the same time.
Yeah, probably. Yeah.
So actually, there is something like really interesting about that, which does not relate to this talk at all or this work, but it relates to another paper. But like basically, So you have a positive result, and but that positive result only holds if you get to see all of the Q star and V star feature. All
right.
of the
I remember
features.
like it requires something kind of some kind of pre-screening over the entire state.
Yeah, so you need to like pre-process all of the states and all of the actions and all the features for it. And if you don't allow the pre-processing, or if you only require the condition of V star and Q star realizable for states that are reachable by any policy from the star state, like this technicality of like maybe V star or Q star isn't realizable for the states that are not reachable from the star state, already that positive result goes away and you have a negative result instead of it. So it really depends on these details.
Yeah, I think that was the one I had in mind. Yeah.
Yeah.
So
yeah,
I guess Chava and I are having some discussion about the point I just made. Is like, I think Chava was saying that with misspecification, you can always work with all possible MDPs. But so that was like a counterpoint to what I was just saying. So it's like, oh, making this assumption constrain the MDP you're working with. But I don't think misspecification is the magical wand here that will do away all the constraints, because this is my suspicion, is that if you actually work with an MDP where this, let's say, linear qπ-Realizability is severely, violated, even with the best possible, however you design the features, then I guess what it means is like the misspecification error is going to be very large, regardless of how you design the features, right?
Yeah,
so
yes.
You could actually have a vacuous bounds even with perfectly, your best effort features.
Yeah, so that's a good point, and yes, the maximum misspecification is what will be relevant here, and yeah, like I could see it very quickly turning really bad if your MDP isn't good to be featurized in this way, right? Like you not only need an MDP, by the way, you also do need the features, right? So yeah, you need.
I guess the problem about the MDP doesn't approximately satisfy the implicitly implied constraint is like that, like you can't even, there doesn't even exist a good set of features that keep the misspecification low.
Yeah, so I guess the way to think about, I always flip between whether or not I think positively or negatively about this. If you believe that there could be a neural network that can that can like kind of learn the important things about the state action pair so that you can fine tune it for any qπ value. If you believe that, then those will be your features. So if you think that is the MDP could be described in such a way by some neural network, then it will be qπ-Realizable. But yeah, whether or not that is a reasonable assumption to make, because yeah, it has to be true for all state action pairs and all policies. So yeah.
Cool. Any other questions from the Chava? Go ahead.
Yeah, I started to type, but I just continuing the discussion, trying to reinterpret what you said. So you're pointing out that Q star realizability and qπ-Realizability are rather different.
Well, qπ all pi, right? It's like actually an all pi part that is.
Well, yeah, like by that we mean, yeah, qπ-Realizability is just a short for all pi qπ.
Right.
But yeah, so they're rather different because for Q star, there is a trivial way of constructing features such that Q star realizability holds, which is Q star. It's like one-dimensional, it's done. For qπ-Realizability, it's not at all very clear of like what's the trivial construction, like what's the
Exactly.
I guess that's a very, very good point. So in that way, qπ-Realizability and relatives are somehow very different. Yeah, got it. Like, so maybe to make it more practical, if one would be given a class of MDPs and then would want to construct a good set of features for the class of MDPs, then qπ-Realizability seems to be much less tractable than Q-star realizability, or like, of course you can be lucky or not, but I guess, yeah, good, very good point. So Gellert, I have to turn this into a question. Do you agree?
Yes, yes, I agree. Well said. Yeah.
Okay.
Yeah, I feel like, yeah, the question is just that, like, do you need the transitions being linear as well that the linear MDP has? Because what seems to be the case is like the algorithms don't tend to like necessarily rely on this directly. You kind of only need it to prove that some targets are realizable. If you only care about your Q values being realizable, because that is like, you only care about your value functions, right? So if you only care about value functions and you don't care about transitions and you don't try to model any transitions, then why should you care about transitions being linear? So the only question is then, like, you know, is that get necessary? That, like, do you need to be able to linearly represent transitions as well to solve the problem, or is that kind of not necessary? And yeah, like, the gap is now smaller between the two settings, but yeah, it is, I think, more directly comparable to the linear MDP literature than it is to the Q-star problem. Because as you say, like, there is a way to trivially parameterize Q-star. There isn't to trivially parameterize the qπ-Realizability.
Yeah. With layer MDPs come all these very nice properties, though, and the algorithms are going to be efficient and, you know, markedly simple. And there is also the question of, like, would you ever want to run these more complex algorithms, or you just like qπ is so close to linear MDP, you just take the algorithm from linear MDP and hope for the best. That might be a terrible idea, or we don't actually know, right? I guess maybe it wouldn't be that hard to construct an example where this would fail, though. But
Yeah, I feel like at least
cases, like if we looked at what the algorithm is doing in that case, like one suspect that things are not going to work well. But who knows? Like, we didn't do this work.
Yeah, we didn't. I think I do agree. Like, it probably shouldn't be too hard to construct adversarial examples. Whether or not it's easy to show that this actually turns up in nature, I don't know. But certainly you could just add like a lot of zero range states and parameterize it in such a way. I mean, it would be more elaborate than the example where I showed the qπ-Realizability holds and linear MDP doesn't. But something like that, and you start running this optimistic estimator, and it will, yeah. I think it should be possible to show that it won't work. But yeah, we haven't done this work, so.
Yeah. Cool. So you were saying, Gellert, something about neural networks as well, like implication.
Yeah, I wanted to make it super relevant and all by talking about how you could hope to connect it with the real world. And I think a very good case for this is like when you have the features coming from this like pre-trained model that is supposed to encode everything that's important. I mean, the whole idea is that you encode the state action pair with a feature representation. And the only thing you should hope for is that feature representation is good enough to be kind of fine-tuned to any qπ. And the way to understand this is if you're just fine-tuning that last layer, what you're essentially learning is this parameter with which you realize qπ. So if you fix all of your network until that very last layer, and then just fine-tune the last layer, then that's just like a fancy way of saying you're learning that last weight vector. So yeah, Csaba, did you have a question on that? Because I just started talking about what I meant by this, but maybe you had a more specific question.
No, I think that. Okay, so following this thought that you started, maybe you're thinking about something like learn the features by exposing a lot of qpy function learning problem to the neural networks. It's like a multitask thing, and then it learns the common features, and then everyone's happy. And somehow just like you need to span the qpy space, and after that you're done.
Yeah. Yeah, so of course we don't have any theoretical results on how that feature learning part works, because that is the magic component that's actually really hard to analyze. We just wanted to look at the linear function approximation part, where you can actually mathematically investigate things a lot more precisely. And yeah, so that part, the feature learning is we just hope that this pre-training thing will give you good features, and that would be one way to get these features. But that's actually just the story behind it.
Okay.
So I have maybe a different question.
Yep.
So do you think you could restrict the set of policies for which you need the realizability property further?
Oh yeah, this I did want to say this thing where one way in which this result is different from how any other result that I know of uses qpy-Realizability is that the other results that would be using a simulator, they would be relying on only the qpy functions being realizable for the set of policies pi that they go through an iterative process. So they iterate, they define their policies pi, and then they need for only those specific policies pi for the qpi's to be realizable. Whereas this result crucially relies on a lot more policies being realizable, and this is because you are so for this tool for the nice functions being realizable, you're basically using realizability properties of policies that the algorithm couldn't even define. Like as it is running, it could not define the policies whose realizability properties it is relying on. It just knows that there exist policies that will have the realizability property. It couldn't define them exactly what they are, but the theory uses the fact that they exist and therefore are realizable. And so that is a way in which this is different from previous results, because it uses the realizability property of a lot more policies. And I don't know how you could get rid of that.
Yeah, actually, Gellert, I guess we discussed that at some point. Is there's a seemingly natural restriction you might apply to the pi's you want to realize. It's for example, all the pi's that are in some sense compatible with your linear Q function, right? But that would actually break all of these. Because we talked about this before. It's in a special case, if your Q functions are if your linear features correspond to something like state abstractions, then all qpy realizability is actually weaker than the bisimulation state abstractions. But we know that bisimulation state abstractions, if you hold on. Yeah, I think we had some. No, I'm not sure, but yeah. In any case, I think that specific case you can still solve, but it's no longer is not going to be a linear MDP anymore.
Yeah. So yeah, I feel like you could make the setting a lot more challenging by restricting these policies that are realizable, and you would need a completely different kind of the tool would basically break, and everything relies on the tool here. So yeah. Essentially, what you need, the tool basically uses the fact that you can learn signals for states where you can make Q value differences, because you can construct policies that actually realize those Q value differences, and you can take their Q differences and the parameters differences will then give you that signal. So you just have to mix these policies linearly with some weights, and that can give you nice functions and realize nice functions. And so the only thing that you can't realize is like functions where there is signal for zero range states or for very, very low range states. There you can't make these policies. You can't even, they don't exist that give you these value differences. So yeah, like if you want to use this tool, I think you have very little hope to restrict the set of policies that are realizable.
I have something that came to my mind, which is like also quite high level. But I was just thinking like the Q or the linear MDP assumption is like a much stronger one than qπ, or it's like closed under the Bellman optimality operator, right?
Yeah.
And then I guess there's also like, Andrea, I think in his paper showed like that the closeness under the Bellman optimality operator does not imply qπ and like the other way around. And it's interesting to see that like here, we take this like weaker assumption of qπ and then show that like it implies linear MDPs, but like with more misspecification, right?
Right. I believe that there is, I don't remember fully, but I think there is maybe a gap in the misspecification. Yeah, like some factor of square or something.
Like the misspecification, I think, goes up, right? When like in your result, like the qπ MDP is like a linear MDP with like more misspecification or something like this.
Yeah, like
and then like,
yep.
Go ahead.
No, sorry. You go for it.
And I was just gonna say, like, it's interesting if the closeness under the Bellman optimality operator, like what was assumed in Andrea's paper, whether you can do like a similar mapping to show that that also somehow implies like linear MDPs. Like, and like, I mean, this is just like a very high level speculation because of just like the pattern I'm seeing, like with no thought about the mathematical intuition, but it's like, yeah, just looking at this relationship, it's interesting.
I think I thought about that once, and now I can't remember what I thought.
Yeah, and another, yeah, actually, you can maybe.
Say it.
Yeah, like it's, I think it was mentioned like just as you were talking about like whether you needed all the policy realization, right? In the sense that like all the other qπ-realizable algorithms that like needed this assumption usually have this like explicit usage of computing the q functions for the pi's. Yeah. And here we like don't really try to do that. Like we use it as a way to like give us really closeness under the Bellman operator, right? Because of the what you need for the targets. And it feels like kind of like a weird like it feels like a sort of indirect step to get to something we know how to work with already. Like that we know that things work under this closeness under the Bellman optimality thing. And then like we use qπ to show that like we can get this with more error than before, but like qπ gives us this, and then we really work with something that works under the closeness under the Bellman optimality operator.
Yeah. So by the way, the more error, the more misspecification. Yeah, it blows up by, if I remember, a polynomial factor. So like for the purposes of this, like we're just saying, yeah, like the misspecification should be really, really small, and like we scale as a polynomial. But yeah, like there are some blow up factors, and they will eventually also be the reasons why like the capital H and D dependence is not that great, and it's still polynomial, but there's a bunch of these steps, these interactions, as you say, that you have to add. But yeah, essentially the kind of motivating idea is that you need to give these like optimistic Q value estimates, and they are going to be basically like your reward sums plus some like you could call them bonus expiration bonuses or like optimistic bonuses. And so these like bonuses that you give to make the Q estimator optimistic, they have to be realizable. And with qπ-realizability, the only functions that you know that are realizable are ones that you can construct as a linear combination of Q functions. And so then it makes sense that what we're looking at is kind of the linear span, like the span of Q functions. But like, like you don't want to add infinitely many Q functions because then maybe your parameter will be infinitely large. So like we have to take care of the size of the parameter. But with that restriction out of the way, it's basically just the span of Q functions that like we can realize, and we have to construct these bonus functions out of them. So that is why the tool comes in, which characterizes the kind of functions that we can construct. And then the only other part is like, figuring out if you constructed a function and it wasn't realizable, then you have to detect that, because like with other settings, you know for sure that what you're trying to learn is learnable with the linearly realizable, and therefore your linear least squares estimator will be good. And here you don't have that guarantee. So the only other thing is you have to detect when this underlying guarantee doesn't hold.
Mm-hmm.
Which, yeah, that wasn't what you asked about. I think the first part is only relevant part. It's just like a fun fact. Yeah.